So in this video I'll be talking about energy methods and Castigliano's theorem. Okay, so module is structural and mechanics and stress analysis, and these are your learning objectives. So these are the topics that I'm going to cover in this presentation. Number one is energy methods, and number two is Castigliano's theorem. So in energy methods, we calculate the strain energy of various members. Strain energy, we will consider three cases. One is strain energy in axial loaded rod, strain energy due to bending, as well as strain energy due to torque stored in a uniform circular shaft. So basically we are going to focus on axially loaded beams and bending of beams, and as well as the torque. So when we talk about strain energy in an axially loaded rod, you can see that this rod has a length of L and an area of A, and force is applied on both sides. So the stress is basically equal to force divided by area. Let's say that this by applying a force, we are basically making an extension of X. So now if you look at the load and extension relationship for the rod, will be a straight graph. So when you apply a force, there will be a elongation X, which is in uniform manner, and the work done is basically the area under the stress strain graph. So the work done is Fx, half Fx, because in the triangle the area of a triangle is half times the two lengths. So the work done will be stored by the rod. So the strain energy is also the same. The work done is equals to the strain energy. Therefore the strain energy UE, which is equals to Fx divided by 2. Now when you recognize the force as equals to stress into area, and also you can write the extension simple x, which is equals to epsilon into L. So you can write from the Hooke's law, stress is equals to strain energy into Young's modulus. So you can take the elongation or extension as sigma divided by E. E is the Young's modulus. So now since we have equated the extension as epsilon L, so you can write therefore the equation is half Fx. So you can multiply half by sigma into A, and also into sigma L divided by E. So by taking the multiplication, we can get half sigma squared E A delta X for an elemental length. So now we will talk about strain energy due to bending. So as you see, the beam bends in the lateral directions, and there is a moment M is applied, and the bending radius is R, capital R. And if you look at the in the this right hand side triangle, you see that this now we will consider this as a there's a angle d theta angle is deformed, and the displacement is dx into dx. So the work done will be stored by the beam as strain energy. So work done is as previously is half moment into theta. This is the force and the deflection. But now if you go to the earlier slide, you can see there's a small deflection d theta, and as you know that ds is equals to r d theta, but this ds is quite small, so it can be equated to dx. So dx is equals to ds, which is r theta. Thus if you take theta to one side, dx divided by r. So but you can write 1 over r is equals to m divided by ei, where m is the bending moment, I is the moment of inertia, E is the Young's modulus of elasticity, R is the radius of curvature. Therefore ub, which is equals to half m theta, which is equals to, when you multiply it by half into m theta, so ub is equals to half m theta, so you can write 1 over r, which is equals to m divided by ei. So you can multiply this everything with theta as well as m. So you have m into theta, which is equals to dx divided by r. So 1 over r you can write it as m into ei. So half m into m divided by ei into dx. Right. So we will talk about the strain energy due to torque stored in a uniform circular shaft later. Thank you.